Okay, good morning, everybody. I hope everyone's having a wonderful day. So just as a quick reminder, remember your assignment 1 is due by 11:59 tonight, but keep in mind that the submission will remain open until 8:30 in the morning tomorrow morning, so Thursday morning. So keep in mind, if you're welcome to submit up until that time, but just be mindful of the fact that there are no late assignments in this course. Just if you don't submit by this time, I may not accept it. Just be very aware of that. So the actual, on paper deadline is 11:59, but this is just some padding just in case if there's anything that comes up on your end. Okay, so are there any questions or anything before we proceed? I will make a note that I'll put out assignment 2 either later today or sometime tomorrow. If we're ready to go, give me 2 thumbs up. Okay, awesome. I see lots of thumbs, man. That's awesome. Okay, so last day to the extent it was, last day we were talking about the worst case analysis for binary search. Then I started shifting over to talking about stacks and queues. So remember that last day I talked about what a container is. A container is just simply a collection. It's just going to contain a collection of objects. And we're starting to talk about a couple of different data structures that are containers. So when I talk about the stack, we had prescribed insertion and remove rules as per push and pop operations, just like my stack of plates, right? Or I could do a push operation, it goes onto the top of the stack. If I do a pop operation, it comes off the top of the stack. Likewise, if I did another pop operation, there's blue plates coming off. So you can think of these as representing the elements that are in the stack. And we can ask all sorts of questions about the stack, such as how many elements are in the stack? Is the stack empty, meaning it has no elements? Or not, meaning it has at least one? We might ask what's the element on the top of the stack without removing it, such as the peek operation, and so on. So we've seen some of these operations. I talked a little bit about how we could represent them, such as using an array versus a linked list. I thought I would talk about a couple other things you could do with stacks. Now this by no means is exhaustive, but I thought I would mention a couple more things we could do. So for example, last day I talked about how we've actually seen how a stack actually can be useful for us. We do things like recursion. We think of the call stack, right? Or our runtime stack, where we push our activation records or call frames onto the stack, and whatever's on the top of the stack is currently the function that is being processed during runtime. And of course, when it ceases, it gets popped off the stack. Likewise, I also mentioned the idea that you could use a stack to perform something like an undo feature. You can think of it having states. Say every time your program moves into another state, you could push that state onto a stack, and whenever you want to undo the present state and go back to the previous state, you can always pop that state off, and you can change your current state to whatever was the one just below it in the stack. So I thought I'd mention a couple other things you could do with stacks. These are things to keep in mind when you're trying to choose a data structure for modeling different activities or processes. So for example, suppose I give you an array A, and I wanted to, say for example, reverse this array. What I could do is I could actually use a stack to achieve this. For example, what I could do is I could scan through left to right through this array, and I could use a push operation on the stack. So for example, if my stack is called S, if I go s.push, and I give it each one of the elements, so suppose that this is inside of a for loop, I could push each one of the elements that are in my array onto the stack. And we'll do it from left to right. So if I do this, notice that if I do a push operation for each one, I'll have 5. 7 goes on top of 5 because now 5 was originally the top of the stack, and I'm pushing this on top of the stack. So presently this is the top of the stack. I have 10, 8, and 1. So if I scan through left to right through the array and I push each one, I end up with a stack that looks like this. So naturally, if I attempt to pop the stack, so if I go through, say I make a while loop or even a for loop, because I know exactly how many elements are in this stack, if I were to make a for loop that scans, that say, for example, performs, say if this is n elements, if I perform n pop operations, so if I go s.pop and get whatever the result of that is, and I assign that to just be what a sub I is, so I just scan from left to right again through my array here, but the thing is, instead of scanning, I'm going to assign whatever comes off the top of the stack to each successive position. What would happen? Let's take a look and see what happens. So I have 5 positions. Remember, I'm not going to clear out this array or anything. I'm just going to rewrite, so I'm going to reassign the values in here. So I got the suggestion of it being in reverse order, so let's see. So if I were to go through my stack, I pop, I get a 1. So if I do that, I remove the element and I return it. If I pop again, I get 8. Notice that 10 currently is the top of the stack. If I ever were to do a peek operation, by the way, it would actually just return me 10, but it won't remove it. So this is not the same as doing a pop. It just lets me take a peek at it just like this. So next I get 10, 7, and then 5. Well, look at it. Look at it. It's in reverse, right? So if you ever find yourself needing some generic way of reversing data in a collection like this, such as an array, you could do this also, a very similar exercise to this using a linked list, for example. You could actually use a stack to achieve this. So if you ever want to, you have a very general way of reversing data, a stack is able to achieve this. The only thing I could mention as sort of a drawback to this approach is that you would have to naturally have this stack, and it's going to potentially contain every element that's in your original container, right? So that means that you may actually have twice as much space you're using when you achieve this. So just keep that in mind. So I just wanted to recap on that. So as the stack processes in LIFO, in a LIFO manner, if the collection of elements are pushed onto the stack, then each, that stack looks a little bit sad there. There we go. Then each is popped the elements are returned back to you reversed. So this gives you actually a very general way if you ever need to reverse data, for example, you can use a stack to achieve this. In fact, you just putting the elements into the stack and then popping them out one after the other actually will give them in reverse order to the way you put them in. This is because of the LIFO rules for how when I do push operations, they go in, and when I do the pop operations, they come out. But they don't, like when I push, right, and I always take off whatever's at the top of the stack, right? Not what came in first, right? So that's why. Another thing I wanted to mention is that you could also use a stack to do other things as well. So, for example, How many of you have ever seen or used HTML before? Don't be shy. If you've never seen or used HTML before, it's something that I know some people, if they're interested in like internet or web, they may have done this before. If not, that's okay. That's okay. The main thing I really wanted to touch upon is that in scripting languages like HTML, you'll very often have these things called tags, and there's a lot of different scripting languages, or even formats that use tags. So, for example, in an HTML file, you may have what we call a tag, something akin to this. So, like you have a tag where it has a label, and then it has a closing version of the label. And very often in an HTML file, you'll have things like such as a head tag and a body tag, and they're opened. They usually use angle brackets like this, not all the time, but HTML, I think it's still the case. But you'd always have a closing one too. So a very natural question is, if I give you an HTML file, or if you think of another one such as XML, how do I know that for every open tag, I have a close tag? The reason why it's important is because when you format your document, like your file that has all of your data in it, for presenting a web page, if you have mismatching tags, the browser may not know what to do with it. So one natural thing you can do with this information is you can pair elements. So whether it be tags, it could be other things like parentheses, like imagine you have a left parenthesis and a right parenthesis, and you want to match them. You can actually use a stack to achieve this. So the idea is actually fairly simple. What you do is whenever you encounter the open tag, or say a left parenthesis, for example, you push that onto the stack. Whenever you encounter its closed counterpart, you pop off the stack. And if you encounter what you should be expecting at the top of the stack, you're okay. So if you have an open one and you're expecting a closed one, you're okay, right? So the idea is that whenever you have an open one, you pop it whenever you have encountered the closed version of it. But the thing is, you'll ask the question of if your stack is empty at the end of this process, or you run into a mismatch. Meaning that you didn't have enough closed tags to match up the open ones. A stack can be used to do this. So you can pair elements. That are enclosed. Such as HTML tags or parentheses. I can't recall, but you may get to see this on the lab. I'm not quite sure. So somebody's asking, in Visual Studio Code, it automatically fills in things like the parentheses, curly braces, angle brackets, or comparisons. Is it using the same principle you're talking about? Off the hand, I can't necessarily confirm or deny it, but most certainly I wouldn't be very surprised if there's some automated process that's just looking to see if there's actually an opposing closed tag or closed parenthesis that follows immediately afterwards. So it might be just the minute you type that, it looks to see if there's another one just a little ahead. If that's the case, then it won't put it. Otherwise, it might. But I couldn't tell you off the top of my head. That is actually a good question, though. But generally, the idea is that you would like to have some general way of doing this. So checking the syntax of a program, or say if you have a script, checking the syntax of that. You could do things like with stacks to check these things. But yeah, no. So I thought I'd mention a couple more of these things you could do with stacks. These are both pretty helpful ones to think about. So are there any other questions about stacks before we proceed to the next data structure I would like to talk about? So we talked about stacks, I talked about how to represent a stack, a couple ways to implement a stack. But up to this point, the question is, okay, so we know what a stack is. What about this thing you called a queue? And remember, the main reason why I'm showing you these two is that they tend to model procedures very often. So processes that are very common, like we ran into like the call stack. we also seen how this can be used for other things. So I also mentioned some other applications, such as if you ever want to use a stack to try solving a maze. That is something you can also do. In fact, it generalizes over, if you take this idea much further, there's actually an algorithm design technique called backtracking that takes this to its wildest extent. But yeah, no, if there aren't any questions, I want to talk about now the other data structure I would like to highlight today. So I thought I would talk about the idea of a queue. So instead of imagining a stack of plates, or say I'm always examining what's on the top of the stack. So whenever I push or pop, it involves the top of the stack. Well, in this container, that's fine. That's last in, first out rules. Well, what happens if instead of having last in, first out rules, I change it to first in, first out rules? So say I have my friends here, again, I have the gang, and they're lining up to get their favorite drink. And I have my lovely green friend here at the front of the line, and I have my dinosaur friend currently at the rear of the line, or back of the line. So the queue is going to model the process of me servicing, for example, my lovely friends here. But here's the neat thing, is that it also can model you can even use this in a more dynamic setting. For example, you can have it where you can even simulate the process of serving, say, clients or customers, or you can imagine as just objects that are getting processed. So this queuing process is a very common thing that occurs, things in such as scheduling. And the idea of queuing itself is a very, very extensive topic in its own right. So, for example, I can also have other things or other people, or people to come join my gang here. So I don't know, suppose Miss Kitty comes here and just says, hey, look, I want to join the gang over here. So say Miss Kitty wants to join the gang. Well, Miss Kitty can't just skip over to where my lovely green friend is, right? Miss Kitty's got to wait at the back of the line. So if, say, that's the front of the line and this is the rear, Miss Kitty's going to have to wait. And I don't know if Miss Kitty wants to wait or not, but the point is that when my lovely green friend is serviced, my lovely green friend could leave the line, and the next person that can be served is the lovely green car. But Miss Kitty then has to wait still some more, right? So I don't know if Miss Kitty wants to wait or not, but she most certainly could wait in line. No, you got to stay there. You got to stay there in line. Yeah, you got to stay behind that dinosaur. So if say, for example, more friends come along and they want to wait in line, they have to wait behind Miss Kitty. What you doing, Miss Kitty? She's just waiting, I guess. But no. So this is going to be the idea of a queue. I guess, no, she had some better things to do with her day, I guess. So anyways, this brings me to the idea of a queue. So let's talk about what a queue is. So a very common way I like to imagine it is that you're going to say I know a lot of people like coffee or go and get their favorite drink in the morning. So imagine you're just lining up to be served at your favorite coffee shop, for example. Well, naturally you wait in the line to get served, right? That's a very common process. So that's what a queue will be modeling, is that when you wait in line, you have to wait until it's your turn. So you have a waiting line, what we'd call a queue, and the idea is that you get entered into the rear or back of the line, the queue, and when whoever is at the front of the queue gets served. And upon being served, they can leave the line. And this is what I'm going to refer to as DQ. So this is going to be, if you leave the line, you're being DQ'd from the front. So the idea is that unlike a stack, where I always perform insertions and removals at the front or the top of the stack, if you think of it as the top of the stack, I'm going to imagine this top of the stack now being the front of the line, and then I'm going to have the rear or back of the line, where my lovely friends can come in and they can wait their turn to be served. So the idea is that you can enter, you can leave the line, but those that are entering or coming in, and they're waiting here at the end of the line. So when you're NQ'd, that means you're entering, and you enter at the rear of the line. And whenever you're served and you want to leave the line, you're DQ'd out of the line. You DQ out of the line. So the idea is that you can also, just like my stack, there's other operations as well. For example, you know how when I talked about a stack, I also talked about this operation called peek, where you can just stare at the top element and I can know what that is. I can just return it without removing it. So I can just, technically speaking, I'll just bring it up and I would just stare at this thing and be like, hey, look, I know that the element is. I can do the exact same thing. So say if I have my lovely green friend here, this is my lovely green friend at the front of the line. Suppose that my lovely green friend was still in the line. I can examine my friend here without having to worry about removing my friend from the line if I need it. So presently, for example, the lovely green car is at the front of the line. I don't have to remove the lovely green car from the line. I could just simply return what it is. We'll refer to this as the front operation as opposed to peek, but they have the same functional purpose. So you're going to see that really the same patterns we had for stacks are going to be apparent here for queues, just the difference is where the insertions are happening here. So instead of it being where it all is happening here at the top, which is now the front, it's going to be that insertions happen at the back over there. So I just want to highlight a few things before we start talking about representing or implementing a queue. So just a reminder, it is a container that's going to follow what we call first in, first out rules, FIFO. It's going to follow FIFO rules for insertions and removals. So this is in contrast to LIFO. Last in, first out, we're going to have first in, first out. So if you're the earliest in the line, you're coming out first. This is in contrast to the stack, like we've seen with our example over here. If you're the first in, you're actually going to be the last one coming out after. So that being said, I want to mention some operations. So remember, this is an abstract data type that's going to support at least these operations. It's going to have the NQ operation. It's just going to insert E, some element E, at the rear of the queue. It's going to have a DQ operation. So if the queue is not empty, it returns the element that is at the front of the queue and removes it. So otherwise, of course, it returns null if it's completely empty. That's at least the convention we're going to use here. But I must stress that, as you may have seen in my example with the array-based stack, there's other ways you can also handle this if you're dealing with different typing that doesn't really relay itself nicely to using pointers. For example, you might use, something called an exception, which I know you'll talk more about in the labs. You'll get some experience getting to use these as well on some of our assignments, which are just where they throw an error and it's done deliberately so that you can handle it. This is in contrast to other runtime errors that might happen unexpectedly during the execution of your program. Those are the two main ones you have. You'll notice that they have very similar structure to them that push and pop have. So notice NQ is like push, pop is like DQ. Just the difference is where the insertions and removals are happening. That's it. That's really it. There's these three other operations I wanted to mention called front. This is just like peek, except you're just going to return what is at the front of the queue. The difference of, it's the exact same idea, except instead of being top, it's the front. Obviously, you return null if it's empty. Size, number of elements, is empty as if the queue is empty, meaning are there any elements in it? If there's none, then it's true. Otherwise, it's false. So it's just like a stack that these last three here. So are there any questions about these operations before we proceed? Is it clear, everybody? Is it clear? Do I need to get Miss Kitty again? Because I don't know where she went. She really got fed up with waiting in that line. Okay. So just think of just a line. So just imagine you're just waiting in a line. And as soon as you see that, really there's a lot of similarities between a stack and a queue. It's just that we have this one little tweak for how the insertions are happening. Okay. So let's start talking about how we could represent a queue then. So I thought I would start off with where I kind of left off last day. So we've talked actually about a linked list based version of a stack. I'm going to show you how we can easily just modify that idea and use it for a queue. There's at least a couple different ways you could represent a queue using a linked list. And it can be fairly natural. I'm just going to make a couple little changes, and you'll see that it really doesn't make much of a difference. Just that there's a couple little complications here that you have to be mindful of. So, let's talk about how we might represent a queue. So the first representation I'm going to show you is called, I'm going to often refer to as a linked queue representation. So we're going to consider the linked queue implementation. So this is a linked list-based implementation of a stack. So it's going to be very similar setup to the one I had for my stack. Instead, now it's a queue. So I'm just going to mention that it's similar. It's similar to the linked stack. So our linked list-based version of a stack. Where now remember, I have a front and a rear to my queue, right? In the stack, I just had the top, right? So it's going to be very natural for me to represent these as pointers that are going to point at nodes in the linked list. Where we keep track of the head and tail. For those that have never heard the term tail before, that's usually referring to the very back end, the very end of the linked list. Of the head and tail of the linked list. Which we'll refer to as the front and rear. Likewise, I'm going to keep track of how many elements I have. So I'm going to have a counter variable that if ever I insert an element in via an AndQ operation, I'm going to increase this counter. Whenever I perform a DQ operation, I'm going to decrease this counter. We keep track of a count, the number of elements. So I can't just spell today. The number of elements. The number of elements. Here we go. The number of elements. So we're going to have front, rear, and count. So front's going to keep track of the head of the linked list. Rear's going to keep track of the tail of the linked list. So I think better than me getting into details, let me draw you a picture first before we start talking about how each of these would be performed. So I thought it would start off by imagining I have a line. Imagine I have a line just like I had over there. So I have all my friends here. I have 4 friends that I'm going to draw out. So this one's A, this one's B, this is C, this is D, this is very D. Don't do this to your friends. Don't just stamp a letter on their forehead. They don't really, usually friends don't like that. So I have this being the front. And this would be the rear. So I have 4 friends labeled A, B, C, D like this. So what I would like to do is I'm going to represent this with a linked list like this. So I'm going to have 4 nodes, A, B, C, D like this. So I'll just write null here. So presently, keep in mind that I'll have a pointer that is going to be pointing at the head of the linked list. So I'm just going to call that front. But you might be familiar with calling that head, or from the linked list based stack, we call that top. And then I'll have another pointer here looking at the rear. And our count currently is 4, right? So this would be, for example, the present state of this queue. Now you might ask, okay, what does an empty linked queue look like? So I thought I would draw you a picture of what that might look like. So this is what it looks like if I were trying to represent this, where I have my line like this. I must note that in its state, when you just initialize the linked stack, the linked queue, when it's empty, it looks like this. You have front and rear. They're just going to be pointing at null. And the count will be equal to 0. So you won't have any nodes yet. You'll just have these two pointers are going to be equal to null. So if when I initialize these in my constructor, I would have front is assigned null pointer, rear is assigned null pointer, and I would say count is 0, for example. So you might ask, okay, so how does the NQ, DQ, how are all these going to work? So actually I have a question for you. So we know what a linked list is, right? So if ever I want to do an NQ operation, based on my picture over here and what we have here and what this looks like it's representing, where should, if I do an NQ operation, say if I want to NQ some element, where should it go? Should it go at the front or at the rear? So far I got one front, I got one rear, I got two rears. Ah, that's okay. Now I got all rears. That's okay. Yeah, no, it's okay. Yeah, if this was a stack, for example, if we were trying to insert, we would put it at the front. But indeed, all we have to do whenever we want to perform our NQ operation, we just perform an insertion on the linked list right here at the rear of, or the tail of the linked list. So notice that the insertions, since I have access to the rear of the tail of the linked list, I can perform my insertion directly right here. Question, if I were to try to do a DQ operation, should I be removing from the front or the rear? Yeah, the front. Very good, very good. So just remember, as long as you remember these two things, these algorithms are actually quite simple, because it's actually quite a lot like what we did with the stack. So let's talk about NQ. Then I think we'll do some examples of doing this NQ operation and see how it mutates the linked list. How's that sound, everybody? So I'll start us off with, for example, with an empty version of a linked queue, and then we'll put some elements in. We'll see what it looks like. So let's talk about the NQ. So we'll have NQ, you take an element E. So here you would create a new node. Create a new node with the data. Remember, our nodes have a data attribute and a next attribute. With the data set to E, and insert this node at the end of the linked list. Via, for those that are not familiar with that phrase, using the access we have to the rear. Via the rear. Now, one thing so question, is there a reason you NQ and DQ in those specific ends? If you swap them, would it still work in the same way? See, the thing is, with the queue, we're trying to represent this process. So if I were to, for example, put them so that I insert at the front and then I remove from the rear, I would have to be very mindful of the fact of what exactly I would like to return each time. I might be getting them backwards, for example. So if I were to attempt to do something like this, I would have to probably change what these algorithms are going to be. Just a little bit. Via the rear. Now, there's one wrinkle to this. Now, do you recall that I can have it where I have less nodes than this? So just as an example, suppose that I do an NQ operation. And remember, when I have this, when I have an empty linked list like this, well, notice that if I just simply insert at the using rear here, I would create a new node. What I would do is I would figure out so I'd hang on to what currently is the rear, if I have a node. Of course, I would set its next attribute to be my node I want to insert into the linked list, then I would reassign the rear to be my new node, right? However, there's this one case we have to be very mindful of, is that when this thing is empty, if I were to insert a new element, say I call it E like this, and I just do that. So I'll call it E. Right now it's just null because I haven't updated its next attribute at all. Say this is the first element I'm putting in. If I were to just use the rear attribute and I say, hey, look, the rear is null, so I'm just going to make that the rear, this node here, for example. If I were to do that, I would update rear to be pointing at this, right? And since I don't have any preceding one, keep in mind rear is not a node at this stage. It's just pointing at null. So notice that if I don't update front, if I attempt to do a DQ operation, if I don't update this is still pointing at null, right? So I would have to make sure I update what front is. So I need to make sure I update what the front is, so it's pointing at this new node, because I don't have any nodes preceding it. So you'll find very often when you're implementing this version of a queue that you have to be very mindful of when you run out of elements, because sometimes the rear might become a case where it's just like there's nothing it's pointing at. Sometimes it'll be that the front is not pointing at anything. So you have to be very careful. So you'll find that most of this process, what we're doing, all I'm going to do is just look at what currently the rear is. I create a new node, and as we're going to see in our examples, all that's going to happen is I'm just going to reassign what rear is after I update the next attribute of what was the rear node. But sometimes if I don't even have a node, I'll have to update the front. So I just wanted to make sure I point that out for you. So if the linked list was empty prior to the insertion, update front to be the new node. And then, of course, finally update the rear, right? Finally update the rear to be the new node. And of course, you got to increment your counter, right? You got to increment count. So I thought I'll go through some examples of me doing this so you get a feel for how I'm doing these insertions. Because one thing I'll tell you up front is that on the next assignment, I'm going to ask you to implement this data structure. I'm going to give you an augmented version that has a couple more operations, and that'll be what you're playing around with on the next assignment. So let me do some examples so you get a feel for this. So let me just go through a sequence of examples here with you. So I'm going to start off with an empty queue, just like I had over there. So I'll start off with just an empty queue. So suppose I have front and rear. So this will be the first thing I'm going to have here. This count is currently 0. So suppose that I perform an NQ operation with an element called capital A. So suppose I do that next. So suppose that I do Q. So suppose I call this Q Q. So this would be on its creation. So this is what happens when I create Q. So when you go Q and then my Q is assigned new linked Q, you'll create something like this. I'll create an object like that. So that'll be what its state looks like. So if I go Q dot NQ, and I try to NQ A and like this, what you would do, just like I said just a moment ago, you'd create a new node. You would, since it was empty, what you do is you're going to update the front and the rear to be pointing at this new node that you created. Its data is going to be A. And of course, I increment count, right? So count is 1. So this is one edge case you're going to have to probably explicitly deal with. So next, suppose that I do another NQ operation. Suppose I NQ an element called B. So I go Q.NQ and I apply it on the element B. So remember, the idea is that I'm going to perform the insertion at the rear of the linked list, which we call the rear or tail. We called it, it's the tail of the linked list, but it's called rear. So remember, I currently have A. So right now I have, just for the sake of walking you through this process, I'm just going to currently have what I have there, and I'll show you how I modify it. So I have null here. So all I'm going to do is watch this. So I'm going to create a new node. Its data is going to be B. Then now before I proceed, because I know the linked list is not, or my queue isn't empty, right? So I know I don't have to update the front. So all I'm going to do is I'm going to hang on to whatever this is. So I'm going to hang on to this. I know what this is. So what I'm going to do, since I know what this node is because I've created it, I have a pointer to it, I'm going to set the next attribute of my node that contains the element A to point at the new node I've created. Then I'm going to update the rear to be the new node. And I increment the count, right? So you'll notice that when the linked list has at least one node in it, this process actually becomes a little bit easier. You don't have this one edge case. So when you're implementing this, just be mindful of the case when you have no elements. When you NQ for the first time, you'll have to update you have to update the front and the rear. But once you have at least one in there, then you know that you can just update the rear. So let me walk you through another one just so that we're kind of clear what I mean. So just so you get a little bit more cozy with this. So I'm going to do another NQ operation. I'm going to NQ an element called C. I'm going to draw the same thing I had over here. So I have A, I have B, and I'm going to create a brand new node C. So remember, this is front right here. That currently is rear. So I create the new node. What I do is I assign the next attribute of what is currently the rear to be pointing at what I'm going to make the new rear. And then I'm going to update the rear. Oh yeah, this is null right here. And I increment count. Like this. So notice that the perk of having access to the rear directly is you don't have to traverse all the way through the linked list. Does everybody notice that? So how do you check if the list is empty? That's a wonderful question. So we haven't talked really about size yet, but I'll give you a heads up. Notice that whenever there is no nodes yet in my linked list, the count is equal to 0, which is equivalent to me asking a couple of different things. I can check if the size of the stack, my queue, is equal to 0, or I could check is empty is true. So if you explicitly want to check if it's empty, you might want to use this because it'll tell you, yes, there are no elements in the queue, which is equivalent to me saying there are no nodes presently in my linked list. But yeah, so no worries, no. So keep in mind that these couple of operations like size is empty, these are very helpful for shortcutting this so you don't have to check for null pointers. It'll really save you time. So I have one more insertion in the notes. I encourage you, if you've not gotten the idea here, to take a look at that one. But are we okay with the enqueue operation? Just remember, all I do is create a new node. All I do is I make the next attribute of what is currently the rear to be pointing at the new node I created. Then I update the rear, and I just increment my count. That's it. Okay, so if we're okay with this, let me talk now about DQ. So DQ, you're going to have to be a bit careful. Like I said before, there's going to be this one edge case you're going to have to be very mindful of. So let's talk about that. So it's going to be kind of like the same idea, but the other way around. This is because we have a front and a rear as opposed to just one attribute we're keeping track of. In the notes, I'll actually have a variant of a linked list based version of a queue called a circular linked queue, which actually only uses one pointer as opposed to two. It's a little bit trickier to implement, but most certainly if you find yourself not a big fan of this whole front and rear thing, that's another way you can go about it. I'll have more details about it actually in the notes just after this representation if you're curious about it. I won't test you on it, but most certainly I want to make sure if you're curious about it, feel free to read about it. So let's talk about the DQ operation. This is the other of the big two. So if you've gotten the idea of how we do a pop operation with a stack, it's going to be very similar to that. Why? Because the front is very much like the top of the stack, right? So if you understand how to do a pop operation with a linked list, the DQ is going to be it's not going to be much different. So let's talk about DQ. So remember, DQ doesn't take any parameters. It just will return to you the element that is at the front, and it removes this. If it's empty, it just returns null. So I'll just start off with that case. If the queue is empty, I'll return null. So like I mentioned just a moment ago, you actually do have a function that's able to do this. You can just check is empty is true, right? So you can actually test this. So this is just one case you have to be mindful of. Otherwise, decrement count, because we're definitely going to get rid of something now. Decrement count, then remove the node at the front of the linked list. And return its data. Right? It's not very much different than what you do with the pop. Like if you wanted to do a pop operation for the link stack, it's not much different at all. It's just instead of calling it top, I call it front. But now you have to be mindful of the fact that you might have to update the rear, just like I did over here when I had to update the front. Does everybody see that? Is that it may be the case that if you don't update the rear, it might be pointing at something that doesn't exist anymore in the linked list. And that's a very easy way to get yourself into trouble with your runtime. Well, during runtime. So I'll just mention update front and rear as per the removal. So this part I'll leave deliberately in a way that I'll get you to think about it as per the removal. So we'll do some examples so you can see what I mean appropriately. So again, like I said, if the queue becomes empty, you need to update front and rear to be null, right? So just ensure that this is the case. So you don't have to explicitly do it. It may actually be implicit in one of the steps you do, but you most certainly will have to make sure that they're updated appropriately. So just be mindful of this. So I'm going to start off with a queue that's similar to the one I have over there, except I'm going to include also, actually, let's do with exactly the one that let's throw an extra element in here. Let's throw D in there. If you're curious about that last step I did not include, that was where I enqueued D in. So watch this. I'm gonna have A, B, C, and D. And what I'm gonna do, just for the sake of time, I'm just going to perform it all explicitly on this linked list. So my count currently is 4, akin to the picture I showed you earlier. Do we have to return first or remove the node first? You're going to have to remove the node first before you can return its data, because remember, if you attempt to do a return statement without deleting the node, remember your function will cease and it will just be like, I'm done here, right? So remember, if you use a return statement, nothing else after that in your function will continue to execute, right? It'll just return whatever you told it to return. So this is why you'll very often see that I'll usually ask you to hang on to or keep track of the element for which, when you do the deletion of the node itself, like just the node itself, not necessarily its data. Well, in particular, in this case, we don't want to actually delete the data in the node because we want to use that. We want to make sure we hang on to that first before we get rid of the node before we return, because that's a step in this process, right? Yeah, it's a good question. But yeah, it's the order. You have to take care of the node first before you do the return statement. So let's do this. Hey, so I'm going to perform a series of dequeue operations. So I'm just going to apply q.dequeue, q.dequeue. So I'm going to keep doing this until this queue becomes empty. So I'm just going to keep applying the dequeue operation. We're going to do this step by step, okay? So I'm going to first remember, whenever I do dequeue operation, the element at the front is what I'm interested in, right? It's akin to the pop operation, similar to my description up here. So if I do a dequeue operation, the first thing that gets returned is what? What gets returned the first dequeue call? So if I were go like X is assigned whatever the result of q.dequeue. Yeah, A. Very good, very good. So when I do that first dequeue call, it's going to return A. So I make sure I hang on to this. I kind of just hang over here and just imagine me, I'm just some goblin over here. I'm just like, I got the A. Yes, I have it. And then I could destroy that node, but I have to make sure I appropriately update the front and rear if necessary. In this case, since the list is not going to be empty, I most certainly can keep by updating the front to be whatever the next node is, right? So what I'm going to do is I'm just going to decrement my count, right? So I decrement the count. I'm going to update my front to be whatever the next node is. in the linked list. And then since I've hung on to this A here, I'm now going to proceed to delete this node. So I'll just go delete on that node. And of course, keep in mind, if you actually want to delete that and the data, remember, if you want to actually delete the data that accompanies it, just follow the pointer, like get the data of that node and delete that. But do it before you actually delete the node itself, because it gets a little confusing. But for us, obviously, we want to return this, so we don't actually want to delete the data itself. But remember, it's just a pointer to that object. So it's okay to actually just delete the node. It'll just delete the pointer. Anyways, so this is how I would perform my DQ operation. Notice I updated front here. So let's proceed. So next, if I do another DQ operation, so remember this is gone now. When I do another DQ operation, what's getting returned next? As I lose my notes. These are usually for show. I just like to make sure you know I'm being careful as I drop things. So what gets returned next when I do this DQ call? So if I do it again, B, yeah, exactly. So I hang on to B, I give it over to me, the goblin, I'll just, it's mine, it's mine. So I hang on to it, I decrement my count, and then I'm going to update front to be it's the next node. And then I delete this node, right? Now I just return B. So let's do it again. What gets returned? What gets returned on my DQ call? C, yeah, very good. So you're starting to get the hang of this, is that all I'm gonna do is I just hang on to this at some point. So I have that. I'm going to decrement my counter. I'm just going to update the front. I'm just going to write front over here because it's starting to get a little bit far away. Though I do like the exaggerated nature of it. So I'm going to update front to be the next node in the linked list. And I delete this. And I just return C. So lastly, if I have to do another DQ, I return D this time, right? See, you guys are pros at this. So I need to do the same thing, right? Hang on to this. So I got D. I'm going to decrement my count. Then I'm going to now do what? What do I need to do now? I don't have a next node. Because when I do this removal, there's going to be no more elements. So what did I say that we should try doing? Yeah, we want to make sure we update. Now, keep in mind, I could go through the exact same process I would have done already. So remember, the next attribute for this node is null, so that I can most certainly update rear to be null, right? It's the issue here is updating the front to make sure it's null. So in this case, we would make sure we update both of these. So I'm just going to kind of cross those out. Instead, I'm going to make them so they're pointing both at null. I'm going to delete that node, and I'll return D. And now I'm back to my empty queue state that I started off with. Does everybody see that? So one thing that just as a big tip when you're implementing this, whenever you get the next attribute, so you get the next node, when you're at the end of the linked list, when you're actually at the rear, when this happens, the next attribute will already be null, right? So the issue here is updating the front. It's very much like my example over there when we were doing NQ. Just the other way around. So are there any questions about that? That's how DQ works. That's at least one way you can implement a queue. Okay, so give me 2 thumbs up if we're okay with this so far. I thought I would intrigue you with another way of representing a queue, but I'll use it as a vehicle to motivate you to look into something for me that I have in the notes. Just because I want to get us to the next topic here soon. But yes, if you're wondering what's coming next for the next assignment, I'm going to ask you to implement this linked queue where it's going to have a few more operations. So that's going to be the biggest part of the next assignment. So you get to have some fun. I know the first assignment we did a lot of conceptual stuff, so I want to let you get your hands dirty doing some code. So, that being said, there's a few other operations I need to point out just before we get to the next thing I wanted to discuss is front, size, and is empty. So these are really easy for me to walk through. So we got these three. They're just like what you would do with a stack, except in front, if the queue is empty, return null. Otherwise, return the data of the node at the front of the linked list. Right? Okay, so question, sorry, just to clarify at the end, rear is already pointing to null and we only update the front to point to null. Correct. So what will happen is, if you actually walk through that same process we did, you notice how each time whenever I did I removed the node, you notice every single time I just simply am going to update whatever the case here would be for the front. I update the front. I think I may have misspoke. I may have said the front instead of rear. But most certainly the idea here is that I need to make sure I update the back of the queue. So the back of the queue, when it becomes empty, if the rear is still pointing at some strange location, that'll become a problem. I think I may have misspoken a little earlier when remember I had the one node left and I had the front and the rear like this. Notice that whenever we did this process, I always updated the front to be the next node over, right? Yeah, I may have said rear instead of front. I may be wrong though. But most certainly the idea is that you need to make sure that the front and the rear are both null. But you'll notice that my process, as I do this every time, whenever I update the attributes, I always get the one that's following next. For one respective side. If I'm doing the NQs, the rear is the one that's always going to get updated. When I have the front for the DQ operation, that's what always gets updated. So you'll notice in that case, the edge case here is I have to update the front. This case will be the rear and the DQ operation. Hey, no worries, no worries. If the front goes to the final node and the final node points to null, does that mean the front is already pointing to null? So if the rear, so let's think about this. So if the rear of the queue is in fact null, that means there isn't any nodes in the queue, right? Because otherwise you'd be pointing at something. So just keep in mind that you have to be very careful with making sure to update the front and the rear because, like I said, and this is something that you'll probably run into if you don't delete the node. I'll mention this actually just right now. So this is one common implementation issue. Is you know how I said, okay, you have the front and the rear. At this stage, they're both pointing at the same node. So suppose that I update the front to be null. So I say, okay, this is going to be null. But if I don't update rear, just being hypothetical with you, this is still pointing at wherever this node was, even if I delete it, right? It's going to be pointing at wherever that was. So this is actually why I'm suggesting you have to update the rear to be null too. Otherwise, you're going to have this, remember, when you come along to do an NQ operation, it might be thinking, hey, look, like this is, you'll keep in mind, it will depend a lot on how you implement it. There might be actually a situation here where you're just going to have it where since the count is equal to 0, it'll be like if this node never existed. But thinking about it from a practical level, this might lead to either this node just sitting out there in memory if you never delete it. If you actually do, it's okay. But you have to be a bit careful. That's what I'm saying, because there's a couple pointers kicking around here. And if you are, of course, dealing with an empty queue, you might actually just straight up just skip over this case entirely, depending on how you implement it. But most certainly, if you're only looking and testing the rear to check if there's something there, the issue here is if you don't update this to be null, you'll see that there's a node still there. And that may not actually be the case when you actually think about it as a queue, because that element was already gone. Yeah, hopefully that clarifies your question. But yeah, a very common thing, making sure you update the rear and the front and the rear appropriately in your NQ and DQ operation when you get to that case where either you're just turning it from an empty linked list to one with one node in it, and one from when you have one node in it to an empty linked list, or respectively an empty queue. It's a wonderful question. Yeah, this is one thing, I swear, if you don't make use of size or is empty, you may run into this issue if you start trying to check deliberately with front and rear the number of elements. Or just checking if it's empty by just explicitly checking the front and rear as opposed to using the counter. Okay. So front, size. So you just simply return count here. And here, of course, you return true if count equals 0. Otherwise false, right? These are really nice and straightforward. You'll find that these three are going to be some of the easiest ones to implement for your class. So if you're looking for kind of a good place to start when you're working on this, when you're implementing this data structure, you can always just play around with these first three if you like, especially these last two. They usually get knocked out in maybe a few lines maximum. So, anyways, let's talk about how you might represent a queue using an array. So I want to use this more of a motivation to talk about just what we can do with a queue. So let's talk about this. So last day I talked about how you could represent a stack using an array, right? So I just want to remind you of that. So another way I could do this is using I'm just going to keep it kind of broader here. I'm just going to give it a title here. I'll call it a circular array queue, but right now I just want to focus for the sake of our conversation here, or our discussion figuring this stuff out together. I want to just talk about an array-based queue. Just nothing too fancy-pantsy, just I want to adapt the idea we had last day for an array-based stack. So the first thing is I'm just going to, like I said last day, I'm going to presume that my array's length is just long enough. And what I want to do is I want to adapt the same idea I had for the link for my array-based stack. So except now I'm going to have a front and a rear counter. So using these, I can keep track of where the front is and where the rear is. For the sake of conversation here, I'm just going to keep track of this as a counter. So I'm going to have the number of elements, instead of it being 1 plus the front, it'll just simply be just some counter variable, just for the sake of discussion. So I'll have a count variable, just like my linked list based queue. This is just to keep things a little simpler for us. So if I were, for example, to start off with an empty queue, if I were to use the same ideas here, well, I would imagine I have a front, a counter variable for front, and a counter variable for rear. That these, if I were to index into them, using, say if this array was called, if I called this array Q, if I want to access a given spot, if I want to know what the front is, I would like to have it so I can just simply go Q sub front if I want to know what the front element is. And I want to be able to go Q sub rear if I want to get the element at the rear. Just akin to what I did last day with my array-based stack. I would like something like this. So if I adapt the same idea I had last time, whenever I do an NQ operation, so imagine I have, say, some elements in here. There's some elements in here. Say I have an array. And just for the sake of conversation here, suppose that this, let's have one more box right beside it. Suppose that all of these have elements in them. This one's empty. And suppose that this is currently the rear. So this is a number that's going to represent the location in the array. Then I'm going to have this one over here being the front. So whenever I do an NQ operation, does anybody have any ideas of how I might go about this? Any ideas at all? So based on the picture, you know that probably the next element that's going to become the rear of the queue would be right here, right? So can somebody kind of walk me through this process of how I might do that? Any ideas at all? Don't be shy. I'm really happy to hear anything. I'll give you a heads up. You'll be very much like what the array-based stack would do. Well, no biting, no biting. So let's talk about this. So what I'm going to do is I can increment. Okay, I got one. Yeah, so when you get to the end of the array, add or replace the last element. Now, I'm not necessarily going to be worried about being at the end of the array at this stage, but in our circumstance, yes, this is the end of the array. So get to the end of the array, add or replace the last element. Yeah, so yeah, you just increment this rear counter variable by 1, and that'll be wherever it goes. And that will be where I'm pointing at, right? Yeah, exactly. So all I do is I increment rear by 1. So I just add 1 to this, and that'll tell me exactly where the next element should go, right? So it's very much like the version for the stack, right? We actually do very much the same idea. Now, let's talk about if I did a DQ operation. So notice every time I just increment rear, and then I just assign where that location would be for my new element. That becomes where the rear is in the array. Okay, how about the front? What would I do here? Yeah, so you get the element, very good. You hang on to that, give it to the goblin, give it to me. Just, it's mine. So give it to me. And then, of course, you can then, what do you do next? So what do we have to do to front? Yeah, you add 1 to it. Exactly, everybody. You get this. So I take this. This will be what I'm going to return. And then I'm going to increment front by 1. And that'll be whatever front will be as a result. Exactly. So you notice it's not very much different from what I suggested the other day for the array-based stack. It's just now I have it where I'm incrementing the front whenever I want to do a DQ operation, and I increment the rear whenever I want to perform an NQ operation. Does anybody see anything interesting about this that might be a bit of a problem? Any ideas? So I want to give you one suggestion about this, and I think this will be a perfect place for us to stop here. So the size of the array doesn't change indeed, but suppose I do a whole bunch of DQ operations. So suppose this one goes, so notice front's going to keep going this way. And notice that all of these are currently being unoccupied, right? Well, it's not necessarily that the front becomes the rear. That's okay. That's okay. But notice I want you to think in the most practical terms. I'm using an array to store data here. Does the rear ever just have the ability to use any of these unoccupied spots? No, right? That's a problem. At least from a practical level, right? Like, we can indeed do this. But that is going to be, like, at least if you're thinking about this, we're wasting a lot of space when we do this. So, a suggestion for how we can fix this is you can imagine I take this array. Instead of imagining it like just it's one straight line, instead imagine it like it's like a clock, like an analog clock. I take this, I form it into a donut, a ring. So of course I could keep making this array bigger, but most certainly I would like to do it when I haven't wasted any more space here. But notice that I'm now wasting space. One smart way to get around this is that you can visualize this array being bent around into a ring, and using modular arithmetic, using the mod operation, we can implement wraparound so that when rear, for example, goes off the end of this array, it'll come right back over here at the beginning. Just like if I form this into a ring like this. So what I'm going to do is I'm going to ask you to take a look at the circular array queue in the notes. I included some pseudocode there as well. I encourage you to take a look at it. And that's actually the last representation I wanted to show you for the queues. This actually is an efficient way of dealing with this array-based issue where I'm wasting space like this. The easy solution to this is I make sure that if the rear starts going off the end of the array, I start it coming back over here. And the way I do this is I use the concept of wraparound using modular arithmetic, or the mod operator, or modulus. So that being said, when we come back, I'll talk about the time complexities for our queue and stack implementations, and address this other issue like our array-based ones that have this capacity called capital N. So I'll deal with these next time, and we'll start talking about sorting algorithms, okay, everybody? So I'll say thank you very much, and have yourself a beautiful day. I'll see you later.